Good afternoon, dear colleagues. Thank you so much for possibility to present my work on VTC 2023. My name is Evgeny Yudin, and I will present my paper, which is called CloudVision DNN-based visual localization of autonomous robots using prebuilt LiDAR point cloud. One of the necessary tasks that needs to be solved for the safe and reliable autonomous control of mobile robots is localization. The task of localization is to accurately determine the current position of the robot in a known map. The most popular sensors for solving this problem are cameras and LiDARs. Those researchers are faced with the choice of which type of sensors to use. On one hand, the accuracy of LiDARs provides greater precision for direct measurements of distances and independence from external conditions such as lighting conditions. On the other hand, cameras provide satisfactory results, but they are less accurate and can measure the distance or only by indirect manner, which can pose a high threat in the case of fully autonomous mobile robot. But if we pay attention to the cost of sensors, we will see that cameras at least are 30 times cheaper. Several researchers have tried to take the best of both sensors to solve the localization problem. The first approach is aimed at direct comparison of 2D lines from the image and 3D lines in the point cloud. Although this approach doesn't require training and is invariant to any scene in which we use this algorithm, it remains inaccurate and not reliable in cases of fully uniform input images. The second approach generates an image from the point cloud and evaluates it with images from the database. This generation process requires a lot of computing power and map persistence in order to provide sufficient quality of localization accuracy. A common disadvantage of learning-based algorithm, its work 3 and 4, is the requirement for retraining for each new area. Since neural networks are trained on 3D map data and learn to find matched point cloud features with specific image features. Main goal of my research is to create a scene invariant approach capable of working over large areas in real-time conditions. First, we have to choose a SLAM algorithm that allows us to build a map from LiDAR scans. For this, several advanced algorithms were launched on Kitty datasets. Metrics of translation and rotation errors shows the best one algorithm. It was LOM. As a result, it was decided to launch it on our mobile platform GermesBot to collect the map. We managed to get a fairly dense map. Visually, the trajectory corresponds approximately to the real one. So my research question is how to achieve higher accuracy of visual localization using LiDAR environment point cloud compared to camera-only methods on large area. I propose a solution that is capable of predicting the position by matching features from the image with a pre-assembled 3D LiDAR map. This approach is inspired by the work of Pixlock, which is aimed at localization by comparing images with 3D structure from motion, which obtained from a set of 2D images. I propose to use a LiDAR map, which is more precision than structure from motion. The advantage of the proposed hike is the ability to collect a LiDAR map with the help of a scout robot only once. Further, this map will be used by operating robots equipped with only cheap cameras. This solution can significantly save the cost of technology and aid in implementing autonomous systems into our everyday life. A robot developed in a robotics laboratory called GermesBot will be used as a testing platform. It is equipped with very high quality sensors for autonomous control tasks. The sensors that will be required to solve the problem are the Velodyne VLP16 LiDAR and the Intel RadSense RGB camera. Nuke and NVIDIA Xavier will be computing models for proposed algorithm. The proposed methodology consists of using two types of robots. The scout robot receives data from camera and LiDAR Data from the LiDAR is needed for mapping of environment. Camera database images are needed for rough global localization. I say about it later. So map and the reference image are saved in database. Next, the operation robot, which wants to know his positions, sends a query image. For a rough estimate of the pose, we need to find the most similar image from the database relative to the query. For this, the NetVLAD neural network is used. With the help of this neural network, we can get global descriptors describing the image. By matching these descriptors, we can know the closest image from the database. This process is very productive since it is possible to get descriptors from database images in advance. Now we know the most similar image from the database and its position. Thus, in order to estimate the pose, we need to find the relative offset between the query and database image. To do this, knowing the position of the database image in the point cloud and the camera parameters, we project a point from our map onto the image. Next, the PixLock network is used, which allows us to extract dense features from the image. Thus, each pixel of the image contains a descriptor. This allows each projected point to be assigned the visual descriptor information and therefore get a point cloud with descriptors. In parallel, dense features are also extracted from the query image. Next, to determine the pose, we project our point cloud with descriptors onto the query image with the extracted features, assuming that the position of the query image on the map corresponds to the database image. Our task is to find such position of the camera that allows us to obtain the correct projections of point, which is determined using the correspondence descriptors of the point cloud and the query image. Using an iterative geometric pose optimization approach, we determine how to change the position coordinates of the query image in order to minimize the reprojection error. When the error becomes minimal, we stop this algorithm and get the desired pose. When collecting data sets, two sequences were recorded. In experiments, one sequence will correspond to a scout robot and the second to an operating robot. The small circle of Scotech campus was chosen as a path. Images and LiDAR scans were recorded for both sequences. This data allow to build 3D map and determine the exact position of collected images. As mentioned earlier, I recorded two sequences. The first corresponds to the scout robot and the second to the operational robot. The trajectory of the robot obtained by the algorithm using the data from the first sequence, green line on the graph, each of 300 images that have been saved to the database, red process, is marked on this trajectory. For evaluation, 300 request images were selected from the second sequence, blue triangles, evenly distributed along the entire trajectory. The LiDAR-based SLAM algorithm is also used for image fidelity. As a point cloud, different 3D structures can be used. This can be a raw LiDAR scan obtained during the collection of the dataset. This can be a map obtained after the mapping of the ALOAM algorithm. In my proposed 3D structure, segment is chosen regarding the visual information from image for avoiding blind area. And this can be the so-called structure from motion that can be obtained 3D reconstruction using set of images. The structure traditionally used for structure-based localization algorithms. On this slide, you can see a demonstration of geometric pose optimization based on 3D map. At the bottom right, they found database image with the help of NetVLAD and the points projected onto it. Top right, query image and 2D search process for the desired position. And on the left is a 3D process where the query image is located in the red frame. During the second experiment, the localization accuracy was determined. 300 query images were used. As the main metrics, the median translation and rotation errors and the percentage of images that include into a certain area error range were used. I compared my algorithm based on LiDAR map with the state-of-the-art visual structure-based algorithm, HLOC and PixLock. Also, I implemented PixLock with a raw LiDAR scan, which I used for mapping. The proposed approach is superior in accuracy to both visual approaches and the approach based on raw LiDAR data. As a result, median translation error is 1.3 centimeter using LiDAR map. Only one pose out of 300 is not in the selected error range, while for PixLock, the number of such poses is equal to 106. The proposed approach is even more accurate than the approach on the structure of raw LiDAR measurements due to a more uniform distribution of points in a 3D structure. Also, the number of points differs by 128 times, which requires a large amount of memory. Also, the size of the resulting map is slightly inferior to visual approach and is only 8 megabytes. During this research, a novel visual localization approach capable of determining the position of a robot in a 3D map obtained using LiDAR-based SLAM was developed. The proposed approach is superior in accuracy to both visual approaches and the approach based on raw LiDAR data. The median translation error is 1.3 centimeter for LiDAR map, what outperforms the best visual localization approaches by 2.5 times. We plan to explore how changing the layout of objects in the area affects their localization quality. When the map differs from the environment perceived by the robot. Although PixLock partially solves this problem by focusing on reliable features, it is necessary to ensure that the proposed approach is resistant to slight changes in the environment. And also, I want to validate the proposed approach on a large outdoor area. For this, it is necessary to collect a big data set. Also, the network can work well in different conditions without retrain. However, it is interesting to test it. So that's all. Thank you so much for your attention.